Hey everyone, hey Maddie, how are you doing? What are we working on today? What do we have? Sorry for the late start there. I was grabbing some lunch. Hey, what's up, HGT? Good to see you here. Mubot is now awake. Make sure I said some tacos. So we have a place here called HEB in Texas, and they sell frozen tacos, and that's what we have. We have for lunch. So I made some lunch, and I was gonna eat it really quick, and I was like, it's too hot, and I was like, I could wait a moment, and I was like, I'll have to stream late. I'll have to wait. Can we do chapter 15? You bet, Maddie. You're here. Chapter 15. Let's make it happen. Let's go look at some chapter 15. Homework or quiz, Maddie? Which one? Homework or quiz? Homework or quiz? We're almost done. 15, 16, 17, 19. Woo! Getting close to done. Homework or quiz? You said homework, actually. So you said homework. I just see chapter 15. I'm like, chapter 15. Chapter 15, homework. Awesome. We got some nulls and alternatives. We've been practicing those lately. So is Friday equation just the Yep. You got HGT. Friday's equation is the intercept because you plug in zeros for everything. Yep. Kind of a trick question there of sorts. So Friday equation is just the intercept. Great job, HGT. Let's hop over to the homework. Okay. This is the first question right here. Write out the null and alternative hypothesis. Well, so the first thing right here, the null always has the what? The null always has the what? Like we should just know whenever we see this, we're testing a categorical variable. The null always has the what sign. The null always has the what sign. Like don't even click the options. Before clicking the options, know the answer. And then you got it down. Because you're like, oh, the null has this. What does the null always have? The null always has the what? What will the null always have with it? Exactly, HTT. Yep. The null always has the equal sign. Excellent work right there. They want to keep his negatives below 62%. So this is what they're trying to show evidence of. They're trying to see if they can keep it below. These are the words they change when you do the question. So they're trying to see if they can keep his negatives below 62%. And that's got it. There we go. Is a 20-sided dice fair? The null has the what? The null has the equal sign. And the dice will either be equal to, like when we roll a certain number, like just a particular side, we'll either get that side 20% or 5% of the time. That's right, 5%. Yep. We'll either get that side of the dice 5% of the time, or we will not get that side 5% of the time, that side of the dice 5% of the time. And by not get, we'd say that the proportion is not equal to 5%, which is 1 over 20. So it's either equal to this or not equal to this, and that would indicate the dice is not fair, because the dice is either fair or not fair. So it is either equal to 1 over 20, or it is not equal to 1 over 20. So that's how we have that one right there. It's either equal to that or not equal to. Only about 19% of people who stop abusing alcohol succeed. Well, let's hope that they can keep doing that. Sellers of motivational tape that claim that listening to the tape recording messages can help people succeed. So they're saying they can help people and be successful. So the null is that 19% of people will succeed. So with the null being 19% of people succeeding, that's what the null is, that it's equal. And what would be the sign right here, Maddie? We're looking for evidence what? They are claiming, sellers of a motivational tape claim that they can help people succeed. They're claiming they can help people succeed, so what would be the alternative for this one? Hey, what's up, Elizabeth? Good to see you here. Feel free to ask any questions. What would be the alternative? These are all categorical questions, like what proportion greater than? Yep. So we go here, we go greater than. Great job. And those are all categorical questions. After a political campaign, pollsters check a dictator's negatives. Why does the dictator care? They're a dictator. They test, I have a dumb question. My brain's a working question on part 1, task 1. It doesn't matter what variable we use to predict it. Yep. Just make it quantitative, Cora. Great question, Cora. Just make it quantitative. So you can just choose something for a simple linear model and just make it quantitative to make a simple model. Yep. Great question, Cora. But choose something quantitative, something that's not categorical. They test the hypothesis that adds produce no change against the alternatives, that the negatives are below this. They find a p-value of this. What do we say? When the p-value is low, reject the null. When the p-value is high, just what? Yeah, we can do some Canvas content quiz. You bet, Elizabeth. Do some. When the p-value is low, reject the null. When the p-value is high, just let it fly. Just let that null fly. So let's go back here. The p-value was high, and so we just let that null fly. And so this would mean we do not reject the null. And it's going to be the interpretation of the p-value here. The probability of our observed results, what we saw in the sample, or a result more extreme occurring given the null is true. So there is a 49.1% chance probability of observing what we saw in our poll results that is this below or lower given there is no change. This is given the null is true right here. If there really is no change, that's the null hypothesis. The null hypothesis is that it is 48%. Yep. So what we observe right here seems very possible given the null is true, because here's the probability of what we saw in our sample given there was no change. So the probability of our results given the null is true occurring in a sample. So that is the definition of a null, a p-value right there. That's the definition of a p-value. So here we go. Let's go ahead and take a look at this. And hey, Brian, can you go over how to write up the success failure condition on the second part of the visualization? I don't see a count. Yeah, Maddie, let's do that next right here. We'll finish off this quiz, and then we will do that right next here. How does that sound? We will do that next, Madison. You got it. So how does this interpretation sound? The coefficient of Sunday is 4. This means that for every dollar spent on Sunday bill, not for every dollar bill. 2 bills that come into a restaurant. So just think about where you have to compare 2 bills that come into a restaurant where one is on a blank and one is on a blank. The bill that is on a blank is expected to be blank or blank. So try HCT, great job right there. 2 bills that come into a restaurant where one is on a blank and the other is on a blank. The bill that comes in on a blank is expected to be blanker than the blank. So try to, you got it. You're on the right track. So just think it's just coefficient of Sunday, has nothing to do with bill amount though. So you're on the right track though. You're on the right track. An organization monitors the aspects of elementary, secondary education nationwide. Their 1996 numbers are often used as a baseline, so they're saying that that's the null. In 1996, 32% of students had not been absent from the school year. In 2000, the responses from, oh my gosh, those randomly selected students showed that this figure had slipped to 31%. Here's a big thing. This is where people make a mistake on this one. It says, do these figures give evidence of a change? This is where the mistake is made. So once again, what does the null always have? The null always has the what sign. So put it in the chat. We should know instantaneously before we look at this. We're talking about perfect attendance, whether or not the student has perfect attendance. So it's going to be P. We're asking, do students have perfect attendance? Yes, no. So it's P. And then we are going to use what sign for the null always? What sign does the null always have? The equals. So we go right here and we say, look, in the equals sign, that means this is the null. Now you should know how to write it out. I was mentioning that this is P because it's perfect. It's proportion of perfect attendance. So we'd ask yes, no, perfect attendance. And then this 32% is used as the P naught. That 32% right here is P naught. Yeah, you got it, Elizabeth. We'll do that. That's going to be right after Madison's question. You got it, Elizabeth. Thank you for asking. We're lining up some questions today. I love it. Here we have the alternative hypothesis. Now, this says, do these figures give evidence, that sounds like the alternative, of a change? Of a change means we're going to choose what? So someone help me out here. What alternative are we going to pick because we're looking for evidence of a change? Should be tomorrow. Great question, Ryan. We are going to be releasing it tomorrow. It'll be due Wednesday for extra credit and Friday for regular credit. So tomorrow, expect to see update on project not equal to Maddie. Great job right there. Yep. And that's because we're looking for evidence of a change. This is the key part of the question to notice that the alternative is what we're looking for evidence for. Condition 1, random. I hit pause. Oh my gosh, I gotta turn off this. Oh God, what have I done? Oh my God. I broke the world. Hopefully we don't get copyright claimed on that. So random and independence are the same sort of condition. If it's random, it's independent. If it's independent, it's random. I pretty much just put them together. It's plausible. It says it's random. Seems independent. 10% condition means that we need this to be less than 10% of all students demonetized. Oh yeah, totally. We might actually get hit. I played that a little bit too long by accident. And this seems plausible. The success failure condition states that we need at least 10 successes, at least 10 failures, and that would be checked via the following way. So this actually relates to the project here. From our sample right here, we would expect 32% successes according to the null, and that's at least 10. And then here's Q naught. So P naught and Q naught. So NP naught, NQ naught. This relates to the project right here because I'm checking to see if I have at least 10 successes, at least 10 failures. So this one's not going to say plausible. We can just check this one, and this one is definitely met. So this is satisfied. It's not plausible. This we just checked it mathematically. So it's n p naught. Here's n. Here's p naught, because that's the hypothesized proportion right here. So we take n times p naught, and there's greater than 10. And then we take q naught, which is 1 minus p naught, and then we times that by n and q naught, and we get this right here. So both of these are greater than or equal to 10, which meets the success-failure condition of having at least 10 successes and at least 10 failures. Now we need to find the z-score. This is where the jump in the question happens, where usually people get confused. They're like, whoa. Find the z-score? Yes. Let's go ahead and take the question and find the z-score. Okay. So to find the z-score, we need to know the right equation. The right equation is going to be found by taking the notation. So it's always about notation. Here we have sample size. Here we have p naught, and as soon as we find p naught, we find q naught. Why is this p naught? Yep, no, that's my first time working this problem. This right here is p naught because it says these are the baseline. And you also know it's p naught just by the way it's set up. So it's saying this is the baseline. It's what we're assuming is true. So also by the way the question's written, whatever value goes right here is p naught. This is p equals p naught. And so whatever value we put right here, it's also in the slides. I can show it. Where's p equal p naught? And yeah, this one, yeah. P equals p naught. Whatever value goes right here is p naught. So this is, yep, chapter 15. Yep. This is p naught right here. And so this means this is 32. So make sure to mark your notation. The coefficient of Sunday is 4.25. When two bills that come to the restaurant, where one is on Friday and the other is on Sunday, the Sunday bill is expected. The Sunday bill is expected to be roughly, and I would not put roughly, I would just put expected to be 4.26 higher than Friday. Exactly. Great job right there, HTT. Two bills that come into a restaurant. If it was a multiple, we would say which are otherwise identical. So if it was a multiple regression, which it's not for this one, you would say are otherwise identical. Great job, HTT. Working in the background. Excellent work right there. Yep. That is a great job. Oh, wait. That's not N. That's P hat. We won't need Q hat for this. We won't need Q hat for this. For this equation, because we're not building a confidence interval, I guess we could put this right home. For this equation, we will do z-score, almost said star by accident, equals to p hat minus p naught over p naught q naught over n square root. And we're just going to plug in the values. So let's magic plug in the values by erasing them. That's a good idea. So we're just going to plug in the values, p hat. This will give us a negative z-score. And over the sample size, 8006. There we go. The z-score is going to be, it's going to be small, like negative 0.89 or something. Something like that. My guess is negative 0.89. I've done a few of these. Watch me be way off. Oh, yeah, square root that. I was like, that looks weird. No, it's going to be like negative 1.9. 1.94. Means we can guess the p-value. I know what that is in my head. Negative 1.92. So we just solved this out right here. That is the answer to the equation. Just make sure to solve it out. The z-score is actually kind of close to something we know. We're doing the does not equals test. So let's go right here, put in the z-score, round down to 2 decimals. There we go. And here's where it gets interesting. You make your brain go, and then you think, and you go 0.056. You get it. Let me show you how I got this right here. We're going to go to Mr. David M. Lane, and I'll explain to you what went on in my head and how I knew that answer. And that's why I say that the empirical rule is so important. So if you're wondering how in the world did you do that, Brian, we're going to see the David M. Lane applet here in half a second. But I'll show you, first of all, how to take this z-score we have, and then I'll show you what I did. So when you have the David M. Lane, which appeared in the chat, we are doing a does not equals test. Because this is does not equals, we will go outside of it. So we need to go outside of this right here. And there, I didn't do outside, I did between. So here is the area outside of it. And I got lucky, it gave me the answer. It said you're close enough with my rounding. So this is the answer. But if you notice, there was some numbers in here to start. Some classic numbers we have in statistics are 1.96. And so you notice these numbers were in here, and that's 95%. So I knew at this point, I knew 5%. Has the question about the... We did that one. We can do that later here. William, you got it. We did that one yesterday. We can do it today, though, too. We can definitely do it. And this is how we get the p-value right here. So stay tuned, William. We can definitely do that. And that is how we get the p-value. And so here's the important part. Here's the alpha level. This is the rejection criteria we are using. Using that rejection criteria, would you reject the null or fail to reject the null? If that is your rejection criteria right here, they're putting a rejection criteria of this. Would you reject the null or not reject the null? They're saying their threshold. You're welcome, William. They're saying their threshold is this, and here's their p-value. So state your conclusion using this threshold right here. Here's the threshold they're using. So state your conclusion using this threshold right here. Using this threshold, is your p-value low? Be very careful because this is not lower than 0.05. Using this threshold, is your p-value low? So just yes or no to that. Using this threshold right here, here's your threshold. You're saying the bar is here at 0.1. Is my p-value low? For the partial F, would you give the test results and focus on whether or not it was... And then that's what I would focus on right there, HTT. You're right. Like the partial F will focus on, and you are correct on this one. You'd focus on for the partial F, is the p-value low? And that would mean that the variables bring with them new information for the p-value being low. I mean, see the HTT, isn't this interesting how all of a sudden this is lower, which means we reject the null. There is evidence that it has changed, because that's what we were looking for evidence for. The alternative is what we're looking for evidence for. We're looking for evidence it's changed. And since our p-value is lower than alpha, we reject the null. When the p-value is low, reject the null. When the p-value is lower than alpha, reject the null. That means there is evidence for the alternative. And this is really getting into kind of 320 world right now with p-values and everything. Do you think this difference is meaningful? It's like 1%, and HTT, you should hear practical significance right here. Like, is this a practically significant difference? It does not indicate large. Yeah, I think so. It's probably not meaningful. So this is practical significance right here, HTT. They're literally kind of getting into the realm of, is this practically significant? We see a very small difference of 1% change. So it is statistically significant according to this standard. But is it practically significant? Not that much. Probably not that important. There's a 1% change, which does indicate that it has changed, but not that practically significant, not that important. Practical significance just means, do we care about it? And someone might care about it. If it went down like 10%, we might be like, whoa, 10% is pretty big and very statistically significant. Topics we talk about in 320, do we care about it? In 1993, a national vital statistics report indicated that 2.6% of all births produce twins. So this is whether or not there's twins produced, that's proportions. Is the rate of twin birth the same among very young mothers? Data from large hospitals found only 9 sets of twins in 478. Maddie, it's time for notation. What do we see here notation-wise? This is a tough one to find out all the notation on. Take a moment right here. We're just going to pause, and if anyone can identify any of the notation, we'll figure it all out. So take a moment here to see if you know any of the notation. I'm going to start writing out the equation to show you what we need. That's what we're going to find. We're going to find the z-score. And the z-score is equal to what? We need p hat. We need p naught. We need q naught, which will be found from p naught, and we need n. So it should be a pretty easy one to find right here. And the issue is, and I'll write it up here. Oh, we need q naught. That's everything we need to find it. For task 1, are we supposed to explain our models or just provide summary? I believe, yeah, you're explaining the partial F. Yeah, we've done a lot of explaining models. So I was like, we've explained a lot of models. So I left that right there. Great job, Maddie. Yep. Maddie identified that this is X and this is N right here. And then this is P naught. That is P naught. So X over N is equal to 9 over 478. And so that's something like 4.2% or so. Sounds pretty different. My brain just does not work today. I can't do fractions in my head instantaneously. You're welcome, Cora. Great job. Lots of great questions today. We're gonna head over. We're gonna do another assignment after this. So we're just gonna plug in the numbers here. Plug in the numbers. Q naught is going to be equal to 0.974. I can do that one in my head, luckily. Haven't lost that brain power yet. So 1 minus 0.26. Yep. Great job, Maddie. Yeah, great job. Excellent, Maddie. That is the practice we need. I keep talking about it's all about practice to when you get to one of these problems, you just say, well, it's telling me what to do. It's telling me the notation. And so now we're just going to plug in 0.1. Oh my gosh. And then we're going to subtract here this. Then we're going to take this times this. And then we're going to divide by this. There we go. I think I broke my code. Send it to me, HTT, via Discord. I'll take a look. Oh, I see I got 9 messages on Discord. You can see right here. I try to keep up with Discord, and sometimes I get behind. I shouldn't have ate lunch. I'm sorry, everybody. I ate lunch, and then I got behind on Discord. I didn't reply. I'm sorry. I'm being sarcastic. If someone was seriously mad at me for like I'm doing P naught times Q naught, someone's like, you did not respond within 2 hours, and you said you usually do that. I trusted you, Brad. I am sorry. I am not perfect. I strive to be. Oh, wow. I love that Z-score. Maddie, that is an amazing Z-score to get because we can guess the p-value again. Why am I saying we have a good guess of the, like, just think about this. We just found the Z-score right here by solving this equation out. Maddie, can you think about what I'm about to do with this Z-score? No, you're not meant to guess these. Remember that we are seeing if it is different, right? So this question wants to know, is this different, I believe? Is it the same, it's asking? So the null would be that the proportion of bursts is equal to this. Good, I'm not gonna block that. And the alternative would be that the proportion of bursts is not equal, because it asks, is it the same? Does this make sense here, Maddie? And what I really like is we just got this p-value, which is going to give me a really good guess at what the answer is going to be. Like, we can just flat out, I think we can get it by guessing it. So I want Maddie to see if she can, it's the last one to do here, and then we're going to hop over some other questions. But we've got everything written out. We've got our null and alternative. We solved for the z-score, and now we just need to find the p-value and reject or not reject the null. If you notice, the z-score here is very low, so we don't really have it. To even help with understanding what the answer is to this, I'm going to draw it out. Here is what the p-value looks like. The p-value looks I hate it when I draw an extra line by accident. I guess technically, I might have done that one a little too close. So we found a z-score, and then we do the reflection of it, which I usually do as a dashed line. Yeah, that might be the exact. You might have gotten the exact. So I think Maddie went and found the exact one. And I would have guessed very close to that. Because what would you have guessed, Maddie, if you just did a rounded guess? Because this is what I was seeing. I was seeing that right there. And we're shading both sides because it's the does not equals. We should point that out here. We're shading both sides of this because we're doing the does not equals alternative. The shading on these tests is relative to the alternative. The alternative is telling us to shade both sides right here because it's a does not equals. And the z-score here is basically -1, and then we just flip that around. So let's go ahead and take this z-score. Are the conditions met? Sure. Random 10% success failure. Good. State the null and alternative. The null and alternative is this. There we go. We wrote that out just a moment ago. Find the z-score. Z-score is this. Round it. Oh, no. There's the z-score. It's negative. Don't forget it's negative. Oh, wow. Look at that. It's even closer. Find the p-value. I'm going to go ahead and just do this and see if it gives it to me. It does. That's what I would have guessed right there. And why did I guess that? So this is why I like using the empirical rule, because it comes in use. Using the empirical rule, this is basically 68%. So using the empirical rule right there, we can see that it's basically 68%. So if 68% is inside, 32% is outside. To get the exact answer, though, you want to go to the applet and input the numbers in here, which I think Maddie did, which is what you're supposed to do. Like, you're not meant to guess every one, but look at the drawing right here, and then look at this right here. This is my drawing of what I thought it would look like, and then this is the actual, like, probability calculated, and you look, it's right next to 1, 68 inside, 32 outside. So that's why I guessed 32, and it was within the margin of error of what the question accepts. You're not meant to guess these, but the better you can guess them, the more you're understanding how it works, and you can draw them out. So I always suggest drawing it out and kind of having an understanding of what the p-value should be close to. So we will, we would give you pictures or something. We'd give you pictures, or on the test, it would be reasonable to ask students, would the p-value be low here? Like, we could put possible answers. Like, we could put like multiple choice guess, like which of these might be the p-value, and we could put 40%, 32%, 20%, 15%. So we could put like multiple choice guess, but since the z-score is like right at -1, what I always suggest to my students is always to draw it out. And it could say use the empirical rule to estimate the p-value. So we could say use the empirical rule to estimate what the p-value would be, and the answer would be basically 32%. Does that make sense, Maddie? Like, we can say, like, using the empirical rule, what would you estimate the p-value to be? Because the empirical rule is super important, and you can use the empirical rule at all times. If you notice, we actually got 2 questions today we used the empirical rule on because the numbers were close enough to it. So this p-value here is high. When the p-value is high, just let the null fly. And that's all we have to see to know the answer, because we're going to use the 0.05 standard to reject or not reject, and we do not reject, and that's got it. Awesome work. I love these a lot more. Like, these are just straightforward to me. Like, these are just like, you do the equation, you do the thing, and it tells you what to do. That's statistics to me. Statistics is like, well, that's the answer. That's what the thing says to do. I think we had, let's see right here. There were a lot of questions. I know Elizabeth had one, but I think we had one right before Elizabeth's. The nutrition. Oh yeah, we have the pregnancy one. Let's up to space. Let's go to space. Put on a little music. This is the sad, chill music as the air conditioner comes on. Oh, we'll yawn right here. Oh. We'll go take a nap. We are getting chapter 14, sampling distribution, ready here. Okay. Here we are. Let's take a look. And then Elizabeth's question is next. After you do the other people's problems, can you do the 15 quiz? Yeah, of course. We'll do that. I think. And someone tell me if I missed anything. We're going to do, who was it? This question goes out to, who was it asked about it earlier? I know there was William. William asked about it, and then Elizabeth asked. So then Elizabeth asked, I think that was the order, right? Okay, then, yeah. Okay, which one was Elizabeth's question here? I'm trying to find it. Nutrition laboratory. Okay, cool. Nutrition laboratory after this one. Let's do it. You can't see it yet. Okay, nutrition laboratory. Okay. So here we go. We've got the human pregnancy problem. Assume that the duration of human pregnancies is a normal model with 263 days. You're welcome, Elizabeth. Thank you for hanging out. With 263 days as the mean and 12 as the standard deviation. Now, this question is actually a review question. Why? Because all we're doing is taking the mean and standard deviation and plugging it into the normal model. So the mean and standard deviation will get plugged into the normal model. Let's bring up David M. Lane in the chat. So if people are wondering, where's that applet? There it is in the chat. And so we're going to plug in those values. I already forgot them, 263 and 12. And we're going to plug them in both spots, 263 and 12. I love seeing people get more and more points. Part of the fun to me of giving out points is like seeing like how crazy amount of points people have. And so, yeah, show up anytime, get some points. We're able to get Stat Nation Brian tier right there. There's tiers beyond Brian tier. There's so many tiers. No one, I haven't even reached the top level yet. I'm not even at the top tier. So, I don't know. Maybe, what tier am I at these days? You'll see higher tiers if I show my points. So we're going to ask the percent of pregnancies between 255 and 270. 255 is about here, and 270 is here. So that's going to be less than 68% because it's in between there. I've got 82,000 points. There's one tier higher, though. Or reset the points next semester. So we're going to go between two values, 255 and 270. So we go to between 255 and 270. This is just single observations. It's less than 68% because it's contained within -1 and 1. So we do know that. Contained within -1 and 1. We throw in our decimal, and we should have that one correct. 1 decimal, it says. Watch out. Don't do that. Well, let's put on a little more music right here. Nice chill music. 35.5. Nice job, Maddie, right there. You can see how many hours I've been streaming for. I've streamed. You've been here almost 10% of the time we've been live. Yeah, 383 hours. I've been on the internet a lot. That's like, it's not even a month though on the internet. I mean, but like, yeah, I know, right? Mubot, that's how long Mubot's been active, and I've been active on the internet here. Not for like the lifetime of the channel though. Good to see you, Iris. At least how many days should the longest 25% of pregnancies be? This is why I entered it into both sides of the applet, is because this applet here lets you put in the percent and tells you the value. Now we can see the longest percent of pregnancies right here, the top 25% of the curve. So now we have the answer there with the longest percent of pregnancies. But this is where the question takes a turn. Happy Thursday. Haslam Friday Thursdays. My goal in life is to help out a school enough that they name the day after me. They call it like Stevens Thursdays. Haslam Friday, because we don't have classes on Friday. So it's already Friday for us. Haslam Fridays. So suppose a certain obstetrician currently provided care to 70 women. 70 women. 70 is the sample size right here. We know previously that the mean was equal to 264, maybe. What was that mean? 263. And the standard deviation was equal to 12. I gotta make sure I get these numbers. Bright A. William Craig, good to see you here. I'm not in class, but you. Oh, that's awesome, William Craig. Glad to hear that. What, are you in 201 or 320 right now? Or maybe you're from the internets. If you're from the internets, then thank you for swinging by. If you ever have questions, let us know. We're doing some sampling distribution of the sample mean right now. So what we're doing is we're saying we know that human pregnancies have a mean of 263. We're throwing out 50 points here for William. Thank you for swinging by, William. We know that human pregnancies have a sample mean of 263. So you would expect a human pregnancy to last 263 days. But the variation around it, like not all pregnancies are 263 days. The variation around it is 12. So, I mean, this is not that unusual. It's in the top 25%. But something over here would be very unusual. That's in the top 1% of length of pregnancies to have a pregnancy that lasts 290 days. So when we think about this, we're now going to do the distribution of the sample mean. So what's the distribution of the sample mean? Well, what we're going to do is we're going to take 70 random women. I mean, this is just, you got to go like, got one, and then we just go here and go, just there we go. So we take 70 random women. I have destroyed this. Should never have done that. Nope, Control-Z does not work. What have I done? So we take 70 random women right here. With the 70 random women, we're then going to take the mean for these women. So with the 70 random women, we then take the mean for these women, which means we would ask them how long was your pregnancy, and then we would take the mean for that. So we'd get data on all of them, and then we'd get the mean for this. And we're asking, if we do this repeatedly, on average, we would expect a sample mean of what? And the answer is the mean. What would we expect for the standard deviation? The standard deviation for the sample mean, and that's what that says, the standard deviation for the sample mean of a sample size of 70 would be expected to be the original standard deviation up there over the square root of n, which is the sample size, which we should mark right here as the sample size. So we can go ahead and compute the new mean, which is still the mean. Think about this. If one person is expected to be 5'10", then what would you expect the average height of 70 people to be? 5'10". But what will change, according to the central limit theorem, is the variation. the variation is going to be the original variation divided by the square root of the sample size, which makes it smaller. So we should 70 square root. So about divided by 8. So we should get about 1.4 or so. 1.4, I'm guessing. How close is Brian in his guess? 1.43. Good to see you here, Grace. If you have any questions, let us know. We're going to do the nutrition laboratory one next. That's 1.4, and I think that rounds to that. 1.4. So let's go ahead and put these numbers in. So we've got the mean is equal to the original mean, and the standard deviation is the original standard deviation divided by the square root of the sample size, and we get this. So now we need to go back to our applet. Let's go back to the applet right here. We go back to the applet, and we change the standard deviation. Notice that this curve now gets tighter, and ignore that it doesn't put the last number there. So it asks, what is the probability that the mean duration of these pregnancies will be less than, and be very careful because it will say less than or greater than, so you have to make sure you know which way you're shading, less than 267. So we go here and we go below 267 and 99.74%. 99.74. And 3 decimals, 0.997. And we've done it. Let's see. That accepts. It's not going to accept that. Ooh, oh, it's so close. It's not going to accept it. It did accept it. I think there's a margin of error about plus or minus 0.003 on that. But the correct answer is this. Well, not that answer. The correct answer was this, and this is obtained from the curve right here, and that's the correct answer. Hello, I created my new variable in task 2. I did build divided by party size, and I've edited it to the data frame. But when I go to print the column head, it says incorrect dimensions. Uh-oh. Uh-oh. Send me it via Discord, and I'll have to take a look at it, Cora. And great job working on it early, so then we can take a look, and I'm sure we'll get it fixed pretty quickly. Great job, Cora. We're going to do, send it to me, and maybe if you're okay with me showing it on here, I could also do that. I think the next question is the nutrition laboratory one. And great job, Cora. Excellent work. Let's hop here to space, do the nutrition laboratory one. Go over to space, turn on all the music. What am I doing? Breaking the screen. Let's see. Nutrition laboratory question. Chapter 14, homework. Okay. I think we found it. Medical researcher. Nope. Nutrition laboratory, we found it. We've done it. Hop back to the news. Okay. So here we are with the nutrition laboratory question. We need to make a 95% confidence roll. So let's first go through and start identifying our notation. Notation, notation, notation. It's all right that we can't see some of those questions. And there we go. Okay. We always practice our notation. So we have here to start 60 reduced sodium content hot dogs will be tested. I have a question about the sampling distribution of the sample homework. Yeah, William, which one do you want to do? Which question would you like to do? I'm going to mark some notation here. Just peacefully marking notation. That's going to relate to the T. That's the sample size. That's the standard deviation of a sample. It's the sample mean. Sample mean comes from a sample size. Number 1, yeah, let's do it. Is that the... And 4, you bet. Is the homework? Yeah, let's do the next here. You got it, William. I think we were out of questions to do, so William, you got it. So we have here the sample size, the standard deviation, and Elizabeth, great job. What is one extra bit of notation? And I'll give you a hint. What is one extra bit of notation that I need right now? So while I write this equation to solve for the confidence interval, what is one extra bit of notation that I have not written, which is very vital to this problem, usually where people get stuck. Usually where people get stuck is that. And what am I solving for right there? So what is that? So usually people get stuck because the T is basically the Z, except every T has this. Every single T always has this. Not the standard deviation. So what is n-1? Remember, n-1 is going to be the formula for the what. Every T has this. And it's for a one sample T. And so I'll start to bring up the applet. I don't think I have it up right now. The applet. Here we go. Let me go grab the applet. It was not here. Here we go. Here's the applet. So that is the what? That is the what? What is n minus 1? Yeah, sure. We can do that. I think that might be the one that yeah, we can definitely do that. You got it, Wesley. I think we'll do that. We got Williams questions next right here. Not the p-value. N minus 1 will be the what? Because we have 60. So this tells us the what for the t distribution. I'll vanish. This tells us the what for the t distribution, which we haven't actually. So that's going to be the answer. Actually, we're making a 95% confidence interval. And here, I'll drop this in the chat. So actually, you know what I can do? I can drop this link, which will actually bring you right to this. So awesome, Cora. We'll do that next. I think Cora's was next. And then we'll do Williams, and then we'll do Wesley's question right here. So does everyone see right here? This is going to be the t statistic for 59 degrees of freedom, which tells us which t we are using. When you change the degrees of freedom, it changes the shape of the t. So this value right here that I'm talking about is going to be the degrees of freedom. So the degrees of freedom right here tell you which t you are using. Does that make sense? So this is a 95% confidence interval created from a t with n minus 1 degrees of freedom. Since n is 60 right there, we know that the degrees of freedom are going to be 59. And watch the t change its shape. Do you see how the t changes shape? Dependent on the degrees of freedom. So if you have very little freedom, it'll look kind of smashed down. Mr. T smashes it down. But if we have a lot of freedom, it will look more normal, and we get this t of 2.001. No, Elizabeth, it's all practice. Let's throw some 50 points. Thank you, Elizabeth. I don't mind if people get questions wrong. That's why I give out points for wrong answers, because it's all practice. This is new material. We're here to practice and just doing everything right there. Is the test statistic the z-score? Yep. Test statistic can be called a z-score. Yep. This right here, wait, this is the wrong question. The test statistic is a z, a t, or a chi-squared. A test statistic is a standardized unit, and we can use them to make confidence intervals. And so technically, I should put a star on this because it's relative to 95% confidence. So that's what the star means there. It's relative to a certain confidence level. We're not solving for t here. We're going to use the t. We just found that this t with 59 degrees of freedom was 2.001, and the degrees of freedom right here was 59. So a t with 59 degrees of freedom for a 95% confidence interval is 2.001, and we see that visually right here. So this is the t statistic for a 95% confidence interval, and the link is in the chat to get to this t-applet. That's probably my favorite visual one to use. So now we just need to go in and plug in the numbers. And let's go plug the numbers. We got Cora's question next right here. So the y bar is 324 plus or minus 2.001. And the standard deviation is 36 divided by the square root of the sample size, which is 60. All of this right here will give us the margin of error. So let's go ahead and find that margin of error. First thing I always find is margin of error. And I'm going to get this right perfectly on the screen. And let's do this. So 60, square root that to begin with. 7.8. Oh, it was off by a decimal. Oh, wait. I don't want to do that. 36 divided by this, okay, times 2.001, so 9.2-ish, yep. And now we just add and subtract. So that's 9.3 rather. Like rounding that is 9.3. We're just going to call it 9.3. Oh my gosh, one of my keys. Gotta be careful there. One of my keys just broke off the keyboard. This is a good keyboard too. 30, so this is 324 plus or minus 9.3. So 324 plus or minus 9.3. And that is our interval right there. So let's go back to the question and take the sample mean of 324 and add the margin of error. 324 plus margin of error, 33333, best number ever. And then 324 minus margin of error, 314.7. Check answer. We've done it correctly. Make sure to use t-statistics there. Where did you get the 2.001 from? Make sure to go to the t-applet and put in the degrees of freedom, and then put in your percent confidence. Does that make sense, Elizabeth? So you go to the t-applet. Here, I'll put the link in the chat again. You'll go to the t-applet to get your t-statistic, and there's the t-applet in the chat. And then from here, you will enter in your degrees of freedom, which are relative to your sample size for a one sample t, Degrees of freedom are n minus 1. 60 minus 1 is 59. 95% confidence, and we're shading the middle portion. Make sure you're using this right here. I don't know what it did to me because there we go. 95% confidence, or like something like 90% confidence. This will change the amount you're shading. Just make sure you're doing negative t to positive t, which does a confidence interval. I wish this just said confidence interval right here, because that's what we would use this for. So that is how we get the t statistic in the formula. What assumptions have you made? Ooh, these are the tough questions. The hot dog weights are going to be, here, I'll re-up here. The hot dog weights are going to be normally distributed and independent. Yeah, they gotta be, we want them to be normal, or at least somewhat normal. It's a tough one. Is the randomization condition met? We don't really know, but we can kind of assume. It doesn't say they were randomly selected. I don't love that question. Is the 10% condition met? Oh yeah. Yeah, 60 hot dogs, unless we're running out of hot dogs in the world. 60 hot dogs is less than 10% of all hot dogs that exist, so we definitely meet that. No assumptions needed there. Is the nearly normal condition met? Probably. I mean, if we're assuming it's kind of normalish, unless it's really skewed. This goes back to the large enough n, nearly normal condition. So we'd be asking, you know, do we have a large enough sample size? So unless it was very skewed, like if I had to write an answer for this, I'd be like, unless it's very skewed, we should meet the nearly normal condition, because if it's skewed, sample of 25 is large enough. So we don't know, but since samples of 60, 40 or more is okay. Yeah. Since the sample of 60 hot dogs is 40 or more. Yeah. So it's saying it's basically good for, I don't love that answer either, but yes. Interpret your interval. I am 95% confident that the true sodium content of these hot dogs is contained in the interval blank to blank. So always practice your interpretations right here. I am blank percent confident that the true blank is contained in the interval blank to blank. Like this one right here. I am 94.5% confident that the true hours of work that students at UT work, that's this interval right here, is contained in the interval 6.89 to 9.22. Or this one up here. I am 98.5% confident that the true proportion of students that are in Greek life is contained in the interval 31.98 to 45.07. And that's a little bit of help for the project right there. And so we are is the same as I am, and we're good on that. So good stuff right there with that question. I think we had, it's Cora's question next. Let's hop back to space. Let's do Cora's question here. A little bit of music. And let's go grab Cora's question. Cora, found it. Okay. Cora, is it all right if I show your work, or I might just answer via this way so we don't show too much. I need to set up a button that like snaps my chats back, which there's ways to do that. So many things to do with streaming on the internet. Yes, of course. Thank you, Cora. Yeah, I always just make sure we have like, do you mind if I show this? It's going to be on the interwebs. Thank you, Cora. Cora says, for test one, created my new variable and have it edited, but when I print the column, it says incorrect dimensions. Okay, let me look. I'm going to run here in the background. I'll probably just put the code in the chat to help you out. Okay, I see what you have right here. Okay. Dividing the variable. I can show this right here. Let me run all the code. Okay, all the codes ran. Let's go back to the main screen. Okay. So what we have right here is we are taking this vector, and we're just going to print this vector to show it. So you can highlight parts of code. I think a lot of people don't realize that. You can highlight parts of code and check it. So we're just running two vectors right there. Do we have any NAs? We do not, so it shouldn't get mad. Now we're taking this right here, and it stores it as X. So X should be a vector stored. X is a vector stored. Now we're appending onto the data frame this. And it looks like it did it. Now, what you want to... Well, there we go. But don't print the whole vector. That'll flood the screen with output. Put it inside of head right here and run this. Cora, try this. Cora, take this right here. So here's what I want you to do, Cora. I'm going to rewind time. Run this chunk right here, or run this code right here, which runs all chunks above. So do that. Run all chunks above, and then run this current chunk right here. And you don't want to print this whole vector out, but if that works, it should work. Tell me if that works, and then put this inside of the head function. You can double click the line, do this. I wish that didn't put it to the next line. I always hate that about doing that. Head actually by default will do the first 6 observations. Does that work for you, Cora? Run all chunks above, then run the current chunk, and it should work. And then put the current chunk, or put this inside of this right here. Yeah. It must have been something improperly stored, but it looked like Mewbot.
I am Mewbot.
Chill out, Mewbot. Chill out, dude. Everyone's checking their points. Everyone's having a good time. Why you gotta be Mewbot? I don't know. Yeah, you probably do you remember writing it differently and then maybe you didn't run the code? There's a bunch of crazy reasons, but great job. Your code worked. You were doing everything right. So that's my answer. I don't know. Sometimes it just doesn't work. Sometimes you're like, why doesn't my code work? Why doesn't my code work? There's a guy. I should talk to him. My hair is green screen a lot better. See, that's where the hair gets weird green screen when you have more like area between your hair. Like if I do this with my hair, then yeah, his hair does that. This guy I watch on YouTube, his hair is a lot more volume than my hair. Yeah, you might have ran the code out of order. That's very possible. That's how things usually just get out of order right there. We haven't listened to Smooth Chill in a while. It's good music as the background breaks. Let's see. We're going to go a whole new background. You ready for this? A whole new background. Probably because I have too many things loaded up. What? Whole new background, not broken background. Out here in space, different space today. I don't like it nearly as much, but I wonder where this background works and the other one just breaks. The questions are now, can we go over Chapter 5's quiz now? I think so. And then did we do all the other questions? We can definitely do that, Maddie. Wasn't there one more, Maddie? Please tell me. Oh, Williams. We're going to do Williams first. We're going to do Williams questions as we watch our new background. I don't know. I don't like it. Whatever. I'll take my broken background. It's much more subtle on the eye. It one's too bright. Let's go grab Williams questions right here as we chill out to some music. And it starts back here in a moment. Just wait for it. We're going to do Williams questions. It was sampling distribution homework 1 and 4. And then Maddie, you got it. We got more than enough time, Maddie, to do those problems too. This has to be just a light variation on a chord with just moving. I feel like it's moving the top note. I need my piano. I like it. Let's hop over here to the main screen. Have you done any more of the Chapter 14 quiz? I think we did some Chapter 14 quiz earlier. Yep, you got it, William. Here, let's hop over. I just got your questions up and going. Let's go check it out. As we listen to some chill music right here. No more coffee. A waitress is believed that their distribution of tips is skewed to the left with a mean of 9.6 and a standard deviation of 5.9. Let's identify some notation. Help me out here, everybody. What do we have notation-wise right here? What do we have notation-wise? Oh my gosh. What do we have notation-wise for this question? We're going to do question 1 and question 4 and then more questions. What do we have notation-wise? Oh, that's awesome, Maddie. Glad to hear that. Hope you're doing well and everything. Glad to hear that. So most people I know, great job. Mu, standard deviation, and N. Great job. I'm confused on this one, part B. You got it, Deanna. Good to see you here. So here is mu, here's sigma, here is sample size. So let's mark these. We have the mean is equal to the mean, and the standard deviation is equal to sigma. I don't know how to draw sigma. I was drawing another mu. And then this is the sample size right here. And so the mean for the distribution of the sample mean is equal to the mean. The standard deviation for the distribution of the sample mean is equal to the original standard deviation over the square root of n. So we're going to go ahead and plug in our numbers right here. The mean is still going to be 9.60, and the standard deviation is going to be equal to 5.90 over square root of 50. It's going to be divided by 7, so 8.82 or something. So 50 square root 5.90. Oh my gosh. There we go. My key is officially 2 seconds here, everybody. Literally, the key has broken off. Stay. Break my keyboard. Hey, what's up, Alan? Good to see you. I'm breaking the keyboard today, Alan. Broke my letter C off the keyboard. Command C, Command V at 2 million times. That's what happens when you do those. So 9.8. Alan, so good to see you. one of our Discord mods, one of the top people on Discord, Alan. Thank you so much for your help. And Stats One, if you ever want to use the Discord, great stuff right there. Cora sent me her code instantaneously. I don't got to hop over to emails and stuff. I can just go right to the Discord and boom. Okay, one last question. When we have the new variable term model, are we just looking for a low p-value to determine if we should keep it or not? Yep. Just see if it helps out. Yep. Just looking at the p-value of it to see if the variable brings with it new information. Great job. I got a really easy version of this one. For this one right here, what is this going to be? If we're looking at, we want to make $500 on 50 tables, well then how much would we want to make on average per table? If we want to make $500, oh, thank you, Alan. You're the best. I mean, I don't say it lightly. Like, Alan, just K-pop and everything, you know you're awesome. So it's Alan sends me some awesome K-pop songs. I love it. Just like checking out the latest and greatest. Exactly, Maddie, you're right, because we're just going to divide this by 50. Check out the new BTS. Check out the new Blackpink. Check out the new Block B. Check out the new Red Velvet. There's so much K-pop out there. 17. What else? Which ones am I missing? To Anyone. I don't know. Big Bang. They don't put anything anymore. Sad times. Okay. So we have here the mean and the standard deviation. So the mean and the standard deviation. Oh, I hope you're doing all right. Yeah. Hope you're doing all right there. That's we just had someone else. Thank you everyone for going and getting vaccinated. That's awesome. Much appreciated. That's helping out the world. We all try to stay safe and help each other out. My brother was tired. I think he got the Pfizer also, and he was tired afterwards, pretty exhausted. I totally watch anime. Death Note, Death Note, L and Kira, yeah, awesome anime right there. Death Note is one of my top animes, I'd say. Great stuff. 9.60 and 0.98. Yeah, check out if you have not seen Death Note. I mean, people are like, anime, whatever. Like, go watch Death Note. If Dr. Stone is great anime too. Yeah, I've heard a lot of people talked about that. So check out I haven't seen Dr. Stone, but check that out. Or One Punch Man, I know people really like too. I think Death Note is a very good, like, if you want to watch a series, go watch Death Note. Like, because it's very, like, it's going to have a start and it's going to have an end. I don't want to give anything away because I don't want to be like, at this point, I don't know. I got the first Pfizer day and then the other little arm soreness have been fine. Good to hear that. Yeah, Death Note is the Breaking Bad of Japan. It really is. It really is like, it's you just go watch it. Don't watch the movies. Don't watch the American made movie. Oh God, don't watch that. Whatever you do, is that Satama? I do not know that one. If that's an anime, I do not know it. Do not watch the Death Note movie from America. Please do not watch that. I'm not just saying that like the American movie. No, just please don't watch it. One last question. When we have the new variable term model, are we just looking for low p-value? That is correct, Cora. Great job, Cora, right there. Oh, it's that is his name? Oh, I didn't know that. I know this much about One Punch Man. I've seen like a tiny bit. Like memes and stuff mostly. Gosh. Well, that's sad, Brian, doesn't it? You're like, Brian, you don't know anime. I don't know. I make jokes sometimes in chat. So I'm like, I watch anime and read manga. We do have some manga. Manga's great too. Read some manga. One Punch Man is a solid show. Yeah, good to see you here, Edward. Okay, we'll focus in on this. So we've got everything identified notation-wise. What's the probability we get at least $500 in tips? So that means we need an average tip of $10. We need an average tip of $10. So we're asking over here, what's the probability we get an average tip above $10? And there it is. That's the probability of an average tip. So people usually, that's the easy part of this problem. The average tip needs to be above $10. So here's the probability. Should be, whoa, what's going on right here? Whoa. What are you mad about, question? Did we not do the standard deviation right? 50 square root. Maybe it was, sorry, I got a little distracted. 5.90. Standard deviation was misentered. That's our 1 today. We get our 1. Standard deviation was misentered. So now the answer is this. Standard deviation was misentered, which drastically... Let me look at that answer. That is not... Something's wrong here. There we go. Okay, the way it was graphing, that was not right. Something looked weird there. Okay, now let's try it. Okay, good. Nice work, it says now. Sorry about that, everyone. Brian, we'll have to review the tape to see what I did. I was estimating the standard deviation to be about 8 point something, and it was 0.8 something, and it was 0.9. But I got the standard deviation wrong, and because I know what the mean is. The mean is 9.6. The observed sample late to the party. Oh, good to hear. Thank you, Michaela. Great job, everybody. I hope everyone's doing well, but great job. Like, awesome job. Like, we're out here to stay safe and keep each other safe. So this is the top 10% of tips right here. Top 10% of tips. Now, I want you to think about this. Got kind of sick after the first dose and second dose, just sleepiness and arm pain. My brother had a small headache after the second dose. I think he had Moderna. Can't remember which one he had. So, my brother's a pharmacist, so he got it like in January. He was way early on. So we see right here 10.669. Now, this is the top 10% what tips. This is the top 10% what tips. This is the top 10% what tips. This is not one table. This is the top 10% of your what tips on a weekend. Because this is not one table. We're doing the top 10%. Oh, and we got it on the other page. This is the top 10% of your what tips. The top 10% of your what tips. And that Y bar right there, not kind of like, it's the top 10%, kind of total. You're kind of right. The top 10% of your what tips on 50 tables. And that gives it away right here because this is a distribution of the what. So this is saying on 50 tables, this would be the top 10% you would what for 50 tables. In the top 10% of time on 50 tables, this would be your what for 50 tables. And this is where the mistake usually happens because you're not going to make $10.66.9 cents or something. What was that? There it is. Yep. So this is your what tip right there over on the left side. That's your what tip. And so we have the notation highlighted right here. So this is the top 10% because you got Iris. We got one more after this from William, and then we can probably do that one next. And then Maddie, I think we will get to. We might have enough time to get to the rest of those. Average, Deanna, great job. So this is your average tip. So if this is your average tip on 50 tables, how would you turn that into how much money you made? So think about this right here. This is the average tip you're making on 50 tables. How would you turn that into how much money you made on 50 tables? You'd say, I averaged $10.66.9 cents on the best 10% of such weekends. So there's the best 10% up here. This is where the value is at. That's telling us where the point is. And this is what we made. I think we did that. I think we did a lot of that on Tuesday. And there's videos. I'll put that in the chat here if this one, Michaela. I'll put the visualization videos in the chat. So what would we do with this number here? Or over there? What would we do with that number to turn it into how much we made on 50 tables? Because that's our average tip on 50 tables on the best 10% of weekends. So if this is our average tip on the best 10% of such weekends, to turn it into what we made on 50 tables, we would do what to it? I'll give you a hint. What do we do with that one right there? Let's just have an anime stream. See, I'm jealous of YouTubers who can do stuff like that. Like watching anime with my YouTube audience. Gosh, you can't really stream anime on YouTube. Someone's gonna be like, do it. I don't want to lose the channel. You stream anime on YouTube, you put your channel in jeopardy. There we go. We multiply it by 50. And that gives us the best 10%, how much we'd make, because that was the on average. We have everything entered in correctly. Good. I was worried there for a second. I was worried. Let me put in the chat right here. If you're working on the visualizations, remember there is the visualization playlist. So we have the visualization playlist. And here is the visualization playlist. We also did some office hours covering them too. But I know straight where the visualization playlist is. There's one going over the proportions and one going over the quantitative. And I think I'll go over all the conditions. So definitely check out those videos or check out office hours earlier this week. And we have question number 4. Oh, I love this question. William, are you still here? We're going to use our brain power for this one. You ready? We're going to figure this out with our brain. This is my favorite question. Good job. There we go. That's how you do that one. Done. Okay, let's get serious here. You ready? Okay. So this one right here, how many points do we need to have the 3 points? Not 3, 2. 2. So it's 3,000 points, I believe. So you can check your points anytime. You need 3,000. And here, William, I'm going to show you how to do this one. And I might talk for a half second how I found that out. But William, this applet I put in the chat right here is the T distribution applet that you're about to see on the screen. So every T has this with it, William. Like every time you hear a T, you must ask me this. You must say, Brian, what is the this for the T? And it's part of this question. Every time you hear about a T, you must ask me the this for the T. So if I were to say we're doing a T distribution, you would say, well, what are the what for this? So every time we're doing a T distribution, you would say, well, Brian, what are your what's for that T? You'd say, Brian, can you tell me the blanks for that? And we'll see it over here in a second. Every time we do the T, we have to ask ourselves, what is the what for that? Every time we do a T. Every T distribution will have with it what's. Every single T, this very important thing right here, every T will have that. Every single T will have with it, that's 29, so we should put in 29 right there. Degrees of freedom, great job, Deanna. And then the degrees of freedom are how basically what it is. I mean, you don't have to go too in depth, but the degrees of freedom here are n-1 for the one sample T. Great job, Channel. Is it Chanel? I think it's Chanel, right? Tell me if I'm pronouncing it wrong. But the degrees of freedom here are n-1, so the sample size would have been 30 for this problem if it's a one sample T. So the degrees of freedom are n-1 for the one sample T. 30 minus 1 is 29. And the degrees of freedom show us how normal it's going to be, like how free it is to be normal. And if you look at this does not look too normal until I start giving it a whole bunch of freedom. Chanel, awesome. Thank you, Chanel. I think maybe mispronounced it once or twice. I'm sorry. If I start fearing I mispronounce stuff, my brain starts going crazy, and then I get really afraid. So right here, the degrees of freedom allow us to see how normal it is. And like we could go into major mathematical theory on all this stuff. We could go into like big details, but for most part, the T and the Z are very similar. They deviate the most when degrees of freedom are very what? The T and the Z will be most drastically different when degrees of freedom are very what? Because you notice we get actually the Z score. Degrees of freedom, when they're very this, will mean the T and the Z are very different. And the T will always be bigger than the Z. Even if it looks like it's the Z, the T will always be bigger than the Z. But when degrees of freedom are very what, they'll be drastically different. When the degrees of freedom are very what, the T and the Z will be drastically different. This is where you see the big difference is not there. But you see the big difference is when the degrees of freedom are very what. And as you get more degrees of freedom, it becomes more normal and you don't really see the differences. Technically, it takes infinite degrees of freedom for the distribution to be completely normal. So when the degrees of freedom are very, very, very small, you see the differences. You see it slowly starts to go into the normal as we go more and more degrees of freedom. It only works when you do it this way because you can start to see it become normal right there and go towards the normal distribution. So we are at 29 degrees of freedom. And the way I do a lot of these guesses is I know the 90% confidence interval is 1.645. So if this was a 90%, was it? Question, you still here? Oh my God, what happened? There we go. 95%. 95% is 1.96. And so we should get an answer a little bit more extreme than that. And the 1.96 has changed. It's gone further out to 2.046. And so the answer here is 2.05. And then the next one, since I know the Z-score for all of these classic intervals, the Z-score for this, so William, here I want you, if I know the answer to this right now is 2.32. So the answer for this is rounded to 2.33. The answer for this is 2.33, and this is basically going to be the same. Like the Z-score for this is 2.33. Does that make sense? And then what do you think the T-score for this might be? Like if you knew, like I know, that the Z-score is 2.33, what do you think the T-score might be? The Z-score for a 98% confidence interval is 2.33. What do you think the Z-score might be? And hint, with this much freedom, it's basically the same. So what would you guess right here? And you're not meant to really guess these, but hopefully you have an understanding that Z's and T's are very similar. The T has with it degrees of freedom. The degrees of freedom control how much like it is like the normal. The more degrees of freedom, the more normal it is. So if we know the Z right here is 2.33, we'd probably guess that the T-score is what? You'll be amazed. You probably will get it right. It's going to be very similar. That's a lot of freedom. A lot of freedom is usually after about 60. Like usually there's very small differences after 60. So what would you guess right here? We can see the answer, but it's more fun to guess. We'll do a few more questions. Since the T and the Z are basically identical right here, but remember, the T is always the smashed down version. Mr. T says, I pay the fool, smashes it down. So what would this be right here? So if we know the Z score is this, if the T score, so this is a concept we should know. So this like implies the concept that we should have in our head is that the T score is always going to have a little bit wider. So it's going to, don't worry, William, right there, let's throw some 50 points out there. I'd like the answer, no clue. That's a great answer. That just shows me like, I don't know. So think about this though. Here's the tip. You ready? It's going to be a little bit bigger. The T is always bigger than the Z. So this is going to be a little bit bigger. So using that information right there with that, I know this is going to be a little bit bigger. What would you change this to? Take any guess you want. It's just going to be a little bit bigger. A little bit bigger. And what would you guess? If I said, it's going to be a little bit bigger than the Z score. That's the Z score, and the T is always bigger than the Z. That's a concept we should know, that the T is always bigger than the Z. The T is always bigger than the Z. Always. But the more freedom it has, the more it's going to be like the Z. And this has a good bit of freedom, so it's going to be pretty close. So what would we guess right here? Do not worry. There's no wrong answers. There's only guesses. That might work. That might work. You might have done it. You got it. I was thinking about 2.38. You got it. It's just a little bit bigger. The Z score and then the T is just a little bit bigger. The T is always a little bit bigger than the Z, but it's more drastic. Let's see here, 78 degrees of freedom. Great job, William, right there. 78 degrees of freedom and 98% confidence. I was thinking 2.38 or so, and you were close enough within the margin of error, because remember I said if we are using the normal, it'll be 2.33, and there's where it rounds to 2.33 with enough degrees of freedom. So the reason I can get these is because I know the answer to the normal curve, so I know these numbers in my head, and then I think, okay, the T score is always going to be a little bit bigger than the Z score. Does that make sense? Is this concept making sense here, William, that if I know the Z score for a 95% confidence interval is 1.96, then I know the T score for anything must be a little bit bigger than that. This is a T with 10 degrees of freedom, but what will this approach as I start to give it more and more freedom? Like if I give it more and more freedom, it'll approach the what number? Like with more and more freedom, this number right here, since this is a 95% confidence interval, approaches this. Enough time for me to ask her? Yeah, no, go ahead, Cora. I think, and then I started a tiny bit late, but does that make sense that this is approaching 1.96? As you give this more and more freedom, the T score will approach the Z score. It needs infinite freedom to be normal, like it never truly becomes normal. But the Z score for a 95% confidence interval is 1.96, so the T score will approach that with more and more freedom. More freedom, the T score will eventually look like 1.96. There's decimal differences, but they're so far back that you wouldn't even notice them with like 10,000 degrees of freedom. So the more freedom it has, the more normal it is. So if I know the Z score, I can usually figure out a close enough T score to guess those. And that's how I do the guessing when I see these. The first one is actually a little bit harder, though, as Cora asked her question. The first question right here, we have to show a non-completed. Oh, we got to go here to. That's hard. I probably, if I get this, it's a miracle. That's a very hard one to guess, but it's not hard if you use the applet. Yeah, so 16 degrees of freedom, 98% confidence. You just go straight to the applet. I will put the applet in the chat again for people. I think it was 16 degrees of freedom, 98% confidence. So we go to the T, 16 degrees of freedom, 98% confidence, and 2.58. I think my first guess was close. Really? This would have gotten it. 2.58. I was really close, but nope. This one I can get, though. That one, it's either, it might be this. It'll accept either, though. With 92 degrees of freedom, that's basically 1.96. We could have, wonder if it would have accepted 1.96. 98 degrees of freedom, was it? Ooh, no wonder I was between 1.98 and 1.99. I'd love to see. You know what? I have to see this real quick, Cora. And this is, so Cora, well, let me put a cut in the video. We'll jump over here to Cora's question. I'm going to use code now to find out, was it 1.98 or 1.99? I need to know the answer to these things. Let's find out. Really quick, Cora, QT, the percentage on the curve. We're doing that. 98. No, that's not right. Oh, is it? It was this. There we go. Wait, what? Oh, it's PT. There we go. Okay, I forgot how to use this for a moment. What? 2 seconds, everybody. Brian's brain broke. Okay, that gets the Z-score. So we want QT. What in the world? That is the percentage below. I might just be giving... Oh my gosh. Wow. There we go. The answer was 1.98. Brian forgot how to use his things. This is the percent below. This is the that. And that's a 95% confidence roll because it would have 0.025 on both sides. Okay, done with that question. The answer was 1.98. It's just that the applet doesn't show enough numbers here, and I wanted to know what this was behind it. It was rounding all of this up right here. It was rounding this up, rounding this up, rounding this up, and that was making it the 5 right there. So I just wanted to see the numbers. I want to know the answer. In task 3, part 2, we have a day missing from a model, but I do not know what day that is. Let's take a look. So when we make a model right here, we have the EX2 data frame, and let's go look at weekday. How many days of the week are there, Cora? So crazy question right here. How many days of the week are there? How many days of the week are there? Now, I know the answer to it normally. Can you go over chapter 14, histogram, description question about the waist size? Yeah, let's do that next year, Grace. You got it. That'll be our last question today. You got it. Thank you, Grace, for asking. How many days of the week are there? There are 7 days of the week, but how many days of the week are there here? That is correct, Corey. You're 100% correct. There are 7 days of the week. But how many days of the week are there here? And the answer is right here. But 4 in this case. But 4 in this case, exactly. So we'll go right here and we'll make a model. And our model will predict tip percentage. I can't remember if that's the very... Make sure to use the right variables. Hiccups. And there we go. What day of the week is missing from your output? What day of the week is missing from the output? And why? What day of the week is missing from correct? And why? That's the question you were asking, right? So Friday... Oh, you bet. Yeah, Iris was asking about that too. You're welcome. Yeah, let's go do that. I think there's 2 waist size questions. Do not the paragraph answers. So whenever we do indicator variables, we always have a reference level. So the reference level is the one that comes what alphabetically. So the reference level is always the one that becomes what alphabetically. So the reference level is always this. It's always the one that becomes what alphabetically. The reference level is always the one that comes this alphabetically. And that would be first. Yep. And that's the reason. The reason Friday is missing is we will compare everything to Friday. So in my family, there's Brian, Darren, and Emily. And so with Brian, Darren, and Emily, who would be the reference child? Who is the reference child in the family and why? Who is the reference child in the family? Who is the reference child in the family? And then you can think about what my coefficient is. And there's the answer. Brian. And why is it Brian? Because Brian comes first alphabetically. Darren's the oldest, but he's not the reference child, at least the way we do it, because it's just whichever one comes first is the reference. Because my name starts with B. Great job answer right there, Cora. That's exactly it. My name starts with B. I'm the reference because no one has a name earlier than mine. And when you think about this, what's the only question you need to know right here to know everyone's age is you just have to ask what? Because to know everyone's age and my siblings' ages, what do you have to know everyone's ages? You just ask one question. Oh, someone was asking. Oh, Sarah just asked. Yeah. Yep. Thank you so much, Iris. Yep, we were just probably about 5-6 minutes ago. How old am I? Yep, so you just have to ask how old am I, and then if you ask how old am I, I'd say I'm 39. You know Darren is now 41, and Emily is now 36, I had to think. So you know Darren is 41. He's 2 years older than Brian. And does that make sense why this is like the reference? Brian doesn't have a coefficient because Brian's no different from Brian. So when you look at the model right here, Friday doesn't have Friday doesn't have anything because it's the reference. This coefficient is how much it is different than Friday. So this right here is the predicted amount for Friday. So this is the tip percentage we would predict for Friday, but Saturday would be predicted to be this much lower than Friday. So 2 days, hits for questions. 2 days that are otherwise we don't need, it's not a multiple. 2 days where one is a Saturday and the other is a Friday. The day that is a Saturday is expected to have a tip percentage that is 1.684% less than Friday. 2 days where one day is a Friday and the other day is a Saturday. Awesome. Thank you so much, Alan. Good to have you here. 2 days where one day is a Friday and the other day is a Saturday. The day that is a Saturday is expected to have a tip percentage that is 1.6843% less than Friday. Does that make sense, Cora? I'm going to do that. Awesome. Great job, Cora. Yep. And so Friday doesn't have a coefficient. It would be these are zeros if we use them as indicators. Hint, hint, practice these interpretations. Yes, Alan is totally serious right there. No, Cora, and thank you, Cora. Excellent work. And thank you, Alan. I don't care. We've been going crazy on points today. We're going to give it another 50 points. Alan, do you have crazy points? Alan might have some ridiculous points if he wants to be like, hey, check out my points. I can't remember if I gave Alan ridiculous points lately. I go fix it later. But I reset the points every semester. So that way, in case you take another class, you have to earn your points back. Does Alan have? Alan should. We'll hop to space right here, and then we'll fix the world. Alan, no. Alan, if you wait 10 seconds. Don't leave yet, Alan. There you go. Alan. Oh, you're beyond the Hall of Fame now, Alan. It might take me about a moment to update, but you should check out those points again. Things change quickly here at Stat 201. I think we have the waist size question. We've helped the waist size. Can you help me with a homework question? Which one, Robert? We might have enough time. Let's figure out. The waist size question we're going to do. Is this it? Let's get some crazy points. Mubot will take a while to update your tier. So if you can leave, I think you had something to do on, so don't worry, leave at any point. Mubot takes a while to update tiers. So I always do it for for students who like Alan just his points, he's not in any classes right now. I know, right? No, but you'll be Mubot. He might, I don't know how often he updates, but he will update you soon. He'll update your tier. So check it out. Your tier will update and you'll be in our highest possible tier, which is a pretty interesting tier to be in. Is this the one, Iris? The one to find a critical T? Yeah, we'll do that here in a moment. We were doing that a moment ago, but we can finish with that too. It's a fun one. I like doing that one. It's one of my favorite ones. No joke. Yeah, we were doing it about 10 minutes ago. Iris, don't worry. Come back, Iris. We're throwing a lot of points today. Is this the one people wanted me to do, or is it the other waist size one? Is this the one? You're welcome, Cora. Great job. Is this the one people... Oh, yeah, we're meeting tomorrow, aren't we? My brain's just broken. We did chapter 14 lecture. Oh, are you in the asynchronous class, Lily? Chapter 14 lecture is already posted. People are doing it, right? That makes me worried. Please tell me I did not forget to hit. I'm gonna have a heart attack if I didn't. No, it's there. It is there. If you're in the asynchronous, about how heart attack. The asynchronous does have theirs posted. We got scared there. You're not in our class? Oh, that's all right, Lily. These simulations do not appear starts like that. Okay, yeah, let's look at that. Oh, thank you so much, Lily. Yeah, sorry, I thought I didn't post lectures for my students, and I was like, oh. I didn't know it. Yeah. Lily, if you want, which chapter are you working on, Lily? Just tell me which concepts, and we'll talk about that in the background here. I think this is the one right here, right? Is this the one, Iris, or is it the other one? Just tell me, Iris, if this is the one or the other one. And Lily, if you need a video over something, just let me know. And thank you so much, Lily, for coming by. Just want to help as many students as we can. If you're working on a topic, just tell me which topic you're working on, and I can link you to some videos that will cover those topics. It's the waist size one on the quiz. Okay, let's get the quiz going here. Let's do the quiz. We got all this code. So, and thank you, Lily. So good to have you swing by. You're always welcome here to ask questions, especially if you're working on a problem. If you're like, hey, how do I build a confidence interval for the mean? How do I interpret this? We can definitely go over any of those questions. We're doing sampling distribution quiz. I am honored that my videos can help out people. I just got scared, Lily. I was like, oh no. I forgot to do that in one moment. My meeting got canceled. Oh, so awesome, Alan. We're just chilling out here. Lily, I think you're the second person just recently who came by and just said, hey, these videos help me out. I really like that. I really like that. I think, is this the one? Okay, let's see here. These simulations do not appear to show. This is not the simulation one. We are not in the right simulation. Is it not? Am I going mad, everybody? It's not that. Is it this one? Which of these? Question 4 or question 5? Question 4 or question 5? Ah, here it is. This one down here, right? Okay, cool. Okay, I think it's this one right here. Pretty certain, because everyone was saying it wasn't the other one. Okay, let's look at this little dude right here. Look at this dude. And what do we see? What way does it... Aw, thank you so much, Alan, right there. We are here to help out. What way is this monster man's tail going? What way is this monster man's tail going? Right to the high, left to the low, whatever way the tail goes. What way does monster man's tail go? Right to the high, left to the low, whatever way the tail goes. What way does the tail go? To the right. Great job, Deanna. So right to the high, left to the low, whatever way the tail goes, lets us know which way it is skewed, and this is definitely skewed to the right. So when we look at these simulations right here, let's take a look at these simulations to figure out the sampling distribution of the sample mean. So I'm going to vanish right here for a moment. So we have here the original distribution over there in the corner. So you can see that. Oh, wrong button. The distribution of single observations is over here. This is the distribution of sample mean size 2, sample mean size 5, sample mean size 10, sample mean size 20. So these are all as we increase the sample size. Now, what happens to the distribution of the sample mean as you increase the sample size? Notice how it starts at 28 and goes to 48, but now down here, it's not as wide of an interval. Also, something's happening to this. Two things occur to this, that it will start to look more this, and it'll also be wetter. As we increase the sample size, going from 2 to 5 to 10 to 20, it's going to start to look more this. You can see it down here. And also, it was really this, and now it's more this. So two things occur to the sampling distribution of the sample mean. As we increase the sample size, the distribution will get more this, which you can really see it right here. You can see this shape right there. So this simulation appears to show that this is becoming a lot more this and a lot wetter. The shape of it gets more normal, and that's part of the central limit theorem. The shape of it becomes more normal. You can see the normal shape appearing. And then you can also see right here the distribution becomes tighter because it went from 28 to 48, and I wish they showed the last numbers on this. They don't. But now it doesn't even go from 28 to 48. It goes from not even 32 to 40. It's becoming a lot tighter, where for smaller sample sizes, it went over a wider interval. That's weird how it doesn't show the number. More normal and tighter, exactly. So these simulations do appear to show it, as simulations would, that the center of the histogram is going to stay the same. And this goes back to our equation that mu y bar equals mu. Less skewness, exactly. Mu y bar equals mu. And where do we have that on here? We have a lot of... Here we go. Mu y bar equals mu. And the standard deviation is equal to the original standard deviation over the square root of n. So the mean is going to stay the same, but what changes is the standard deviation, and that's where we divide by the square root of whatever the sample size is, making a smaller standard deviation than the original standard deviation. So we're going to see here the histograms approach the normal shape, and the means, so the variability in the means, decreases. The variability, which is standard deviation, the histograms are fairly normal when they reach a sample size of 5. Good stuff right there. I think there was did people want to do the T stuff one more time? We'll do this real quickly here. Great officers, everybody. Hey, what's up, Monster Man? Oh no. I feel like I scared off people. No. Chill music with Statua 1. Let's go right here to chapter 14 homework. And here we are. My favorite question to end the stream. Okay. We'll see if we would have gotten it. Okay. We all back. Okay, so this is finding the T statistic. Great job, Iris. You're welcome. Thank you for swinging by. We're just here to do some work and learn some material. Great work. Hard work, everybody. Solve the problems. This one has very little, and so someone might be watching this video and gone to this part. The T and the Z are basically the same. Basically. The T and the Z have more drastic differences with smaller degrees of freedom. Every T distribution has with it what are called degrees of freedom, so you know which T you're using. Let's bring up our T applet. Here's the T applet I like to use. I'll put it in the chat. So if you're watching, it's in the chat now for you to go to the T applet. So whenever you get a T distribution, you must first ask, what are the degrees of freedom? For one sample T, the formula is n-1, which is sample size minus 1. It told us in this problem that the degrees of freedom are 10. So just flat out said those are the degrees of freedom. This button right here is used for confidence intervals because confidence intervals shade the middle percent of the curve. Like we're shading the middle blank percent. And if it was 95%, we found the answer. 98%. So the 98% confidence interval is going to be wider than the 95%. So you're going to see as this goes to 98% of the middle of the curve covered, and we got 2.76. And that should do it right there. And then this one right here, I want to guess it. Alan, you are just in the Goku tier now. Told you it would happen. And so we're now at a 99% confidence interval with degrees of freedom 82. We go back to our applet. We made all these. Was it 92 degrees of freedom? 82 degrees of freedom. And I think it was it 90? 99% confident. And there it is. Even wider interval. I'm over 9,000. We started off with some Dragon Ball Z, some memes earlier today, and now we're back into the Dragon. We just call it like our meme tier. Yeah, meme tier. That's what it's called. We made this up a while ago. And so you're in the highest tier. You've entered meme tier. Yeah, 5, 7, 5, 8. I'm always trying to remember my T scores and Z scores. So just to end, the reason I know a lot of these off the top of my head is I know the Z score for most confidence intervals. So if we go here to Q norm, yeah. So your next tier should be Saber, Archer, Caster. What is that from? What is that from right there? So I'll tell you the answers to these before they appear. This will be 2. Well, I guess we'll do it this way. Fate is Fate an anime? I think I've heard of Fate. Sounds familiar. Or is it a game? Like, tell me what Fate is. So this will be 2.5758, 2.5758. This will be, and it's on the screen, so I'm cheating because I can see it, 2.3263, 2.3263. I don't know 96%. More like 2. I have to guess this one using my knowledge. 2. It's an anime. I'll have to check that out. Yes. Fate Zero. Oh, it sounds familiar. It just sounds so familiar. I say this is 2.12. Oh, man. I was way off on that one. Classic right here is, now I'm going to do it more exact, 1.9599. There's only 2 animes. No, just kidding. There's Trigun and there's Full Metal Alchemist and Cowboy Bebop. And yeah, a lot more. This will be 1.9599. There it is. 1.95996. Yeah. I like knowing the extra decimals. It's not 1.96, it's 1.95996. So extra decimals. This one right here is 1.6449. There it is right there. It rounds to 449, 1.6449. This one right here is that's an 80% conf roll, so it's 1.2812. This one I get wrong sometimes. I think it's 1.2812. 1516. It's 1.2816. That last decimal just switching around my head right there. I gotta know things to the 10,000th digits. Gotta, come on. Then I also know this one. This one I just don't use this one nearly enough. This is the IQR though. So since this is the IQR, this is 0.673. 673 something and then 2 maybe. 6744. Come on, Brian. 6745. Okay, put that in your head. I knew it was 67. It's basically like 2/3. You can think about the IQR as basically 2/3. And then if you go here, this one is obvious. We can do this one as many decimal places as we want because the answer for this one is this. This is the 50th percentile, and the z-score for that is 0. And so all of this you don't need to memorize, though. There's no point in memorizing all that because you can go right here and you can get every single answer we were just showing on the screen for the low price of just entering it into the applet right here. It is rounding it. Oh, we're on. Yeah, we are on. Correct. That was that one. Yeah. So you can get every single answer we were just showing on the screen by just doing this. It is rounding it. There's the 20. We didn't do a 20%, but all these answers right here. You do not need to memorize them, but you can if you want. Because, I mean, memorizing stuff is fun. I'm weird like that. I like memorizing stuff. And then I fail at it. But yes, well, with that... Oh, we forgot the other one. There we go. That's what started it all. 2.5758. Well, with that, everybody, let's hop back here to space. Let's play one of my favorite songs here to end. Is it 80s Classic? No. No, I like that one, but... It's one of my favorite, just crazy 80s songs. We're going full Hacker Man mode right here. We're doing this. Got some anime in the chat. Hang out in the chat here. I'll let the stream go a little bit longer. We're ending right here with Hacker Man and bringing it back to the 80s. I'll see everyone later. Bye for now. Tiny Brian says bye for now. Bye, buddy.
Hey.
Got the wrong voice on. We got people talking about death. Now we got one last question here. We got it. Where's that waist size question? Let's get that waist size question going here. Cool, let's do this. Let's knock out one more question here. We got this. One more question. Let's make it happen here. One more question as we talk about some anime in the chat. Let's do this. Let's make it happen. Okay. We need more chill music. You ready? Let's do this. Here we go. With this question right here, it gives us... you're welcome, Edward. Anytime, man. We're here to help out. Like, unless I was... you did it just in the nick of time, because if I'd hit the stream over button, it would have stopped streaming. And then, I mean, I could have started a new stream, but it would have been, like, confusing. But I was just chilling out, so... I was like, well, we got this. Let's put on a little music. Let's chill. Notation. So I need your help here, Edward. With this question right here, we need to identify the notation. Okay. Any of the notation to help out right here. That and that. And these. What are those? So what do we have well, that tells us what that is. I'm going to start writing some equations, see if you can identify any of the notation while we do this. The mean for the distribution of the sample mean is equal to the mean. The standard deviation for the distribution of the sample mean is equal to the original standard deviation. I guess we can call it that. They call it SD sometimes. Standard deviation is equal to the original standard deviation over the square root of n. Well, and you're right, it is quantitative. Great job. That means we'll have the nearly normal conditions. So this is quantitative. These numbers right here are going to be key to solving this. Those numbers right there are going to be huge. So what are these numbers? You would think it wouldn't do it unless I connected those. So what are those numbers? What is this? What is this? What are those? Correct. This is sigma, and this is mu. So we actually know the answer to the mean. You want to see something awesome? This will be like mind blown right here. That's the answer to everything for those questions. Now this one is going to be relative to the sample size. We'll want to put in the sample size right here. It's more 80s. It's all 80s today. So whatever, we have to change that, and this is 3.99. That one, we'll have to change this relative to the sample size. Does that make sense? So the sample size, as it increases, will make a smaller standard deviation of the sample mean. Does that all make sense, Edward, right here? As the sample size increases, we'll have a smaller standard deviation of the sample mean, where up here, the mean for the distribution of the sample mean will be equal to the mean, which is always this number, obtained from this right here. So the standard deviation, though, will be dependent on the sample size, which we will have to input each time to solve. So let's go ahead and hop back to the problem. Awesome job, Edward. Great job. So the mean, well, the mean is this. Do not look at the simulation. Don't look at that. Don't look at that. That's the mean. Boom. Solved. Why is that the answer? Because the mean for the distribution is the mean. And this is the mean, so the mean for the distribution is the mean. And this is the theoretical mean, not the simulation. The simulation might show what's true, but it's just a simulation. It's just showing us possibilities. Like, we simulate possibilities. This is theoretically what is true. And once again, just to reiterate, it's like, well, wait a minute, I see that over there. Well, it's just a simulation. Theoretically, what is true is that the mean for the distribution of the sample mean is equal to the mean, and this is just a simulation to see what we saw. And we saw numbers kind of close to it for the most part. Which is going to be what we answer later. So now, once again, these numbers will be slightly accurate because they're via a simulation, but we're going to take our original standard deviation divided by the square root of the sample size. We got one more 80s song right here. 80s fun. We already did that one. 80s classic. We take square root of 2. Okay. Yes, theoretical standard deviation. So take this and divide. We're going to square root it. Watch what I do again here. 2 square root. Does that make sense? Yeah, sure, Cora. Ask away. Ask away. 3.99 divided by square root of 2. Copy, paste. We'll worry about decimals here in a moment. Square root of 5. 3.99 divided by square root of 5. Copy, paste. We'll worry about decimals in a moment. 10 square root. Just don't make errors. 3.99. Just don't get hit. And 20 square root. We're just doing the square root because it's sigma divided by the square root of n. I'll show that here visually in a second again. Oh my gosh, this key is broken. Let's copy it again. Might be buying a new keyboard. I like this keyboard. I've been very happy with it. We didn't, luckily, woo! The rounding worked out. To determine if the variable weekday is significant, do we just look at the p-value of the overall model, or do we look at the p-value overall model? Yep. Indicator variables will show you the difference from the what. Indicator variables, and this is a key concept for the test, indicator variables will show you the difference from the what. And these values are very similar, and that means the simulation is doing what it should. For the sample sizes, theoretical values, nope. Yep. I think it's right. Yep. Ooh. Ooh. I've gotten this one wrong before. This is 5. Okay. I don't love that question. So they're asking at what point it'll be from the reference level. So the p-values for your model, Cora, is all reference level p-values. Or the p-values for indicators are going to be the p-values for difference from reference level. Does that make sense? P-values for indicators are the difference from the reference level, and if they're statistically significantly different from the reference level. Yep. So then the p-value for the model, since we only have the one variable in there, is the significance going from the naive to the full. Yep. That's exactly right, Edward. You take your... Here, we'll show it again right here. So you can see it right here. You're just going to plug in these numbers right here and do it And so these numbers will be kind of close. Like if you get like 4 for this, then you'd be like, wait a minute. So these can be used as a reference to see, but those are not the right answers. They could be, but those are not, like, they don't have to be the right answer. Does that make sense? Like, use these as kind of a guideline. If we look at our answers right here, I got 2.82, kind of close, 2.178, kind of close, very close on that one, and they get really close. But they don't have to be the answer, but they're kind of a guideline because the simulation is going to show its reality. This question right here is the most unfair question out of all of them because it's a judgment question. Gotcha. Oh, awesome. And I could see how someone could say 10, but I mean, for the most part, this is normal. Sorry, Mike Pearson, but I would say 10. I know the answer is 5 because I've done this question a ton of times. But when you look at this, when do they appear to make the normal distribution? Because we're looking at the distribution of the sample mean of sample size blank, blank, blank. That's what we're doing right here is we're increasing the amount of observations we're taking from the parent population to make the distribution of sample size mean 2, sample size mean 5, sample size of mean 10, sample size of mean 20. So each observation in here is a mean of 20 single observations. And they're saying 5, I say 10, but my Pearson gets to pick the right answer. So it's 5. The distribution of the original shape is pretty normal. It's unimodal and mostly symmetric. It's not perfectly symmetric, but it's definitely not bimodal. A bimodal would mean it had 2 bumps. Uniform means it's flat. That's uniform. And we already said it's not bimodal. I'd rather say it is unimodal. Oh, nearly unimodal and symmetric. They're saying like they should put unimodal and nearly symmetric. And once again, to see that shape, where'd you go? Really? Oh, we got to see it right here. It's left skew, but it's definitely unimodal. Unimodal left skew. That's what I wish it would say. So it does not take a very large sample size to make it normal. And we've done it. We get to do our favorite question again. 2.06. Nice work. 99. 2.59. Oh, no. Come on. 6.2. Last try. Of course. There we go. It's a bummer to me when we don't get it right. This is the hard one to guess. This is the hard one. And I got the hard one right last time. Oh, no. Last guess. Woo! Oh gosh, this one is nearly impossible to guess. I'm gonna get it. Do one more attempt at this. This is sadly, I enjoy these things. That one's easy. 90%. We can get this one. That should be about right. Oh, come on. That's close enough. It's got to be a little lower then. Yeah. That had to have been right at the edge of what it would accept. Keeps doing 99, which is one of the harder ones to do. That is a harder one. 98. It's tough too. This is the tough one. This is me having fun. Such a tough one to guess. That one we can get. The second one has more degrees of freedom, so it's way more normal. That's how you practice your mathematics. There we go. This one's easy. I would bet everything on that. That one's very easy. Last try. But have you done the homework talking about carbon monoxide? Do you want me to send you... Email me, Edward. Do you want me to send you the link to that one? I'll hop off here because I'm going to get ready for class. Do you want me to send you the link for that one, Edward? Send me a quick email and I'll send you the link for the monoxide one. You know what? Let's go find it. I'll put that here at the end. Sorry, I got distracted by it. It's seriously like a video game to me. That's kind of, that might be sad. Man, Brian's a nerd. Got 9 people watching me just solve problems endlessly here. Have I been putting these in the playlist? Oh, gotta make sure we have All-Stars playlists. Updated 2 days ago. Didn't put those in the playlist. Carbon monoxide. CO2 problem. Here, well, let's bring it down here. CO2 problem. No, hold off here. Oh, this is this morning. That's why it doesn't have stamps. Yep, here it is. Here you go, Edward. There you go. So this is the video right here. Oh man, 770 views. That is awesome. There's the waiter tips. Here's CO2 emissions. Go through, identify the notation, and then solve out the distribution. There we go. That's got everything. We'll head off here. Let's put on a little 80s music. I decreased the size of my video thing. 2 seconds, gonna fix this. Look at that. Back to the normal size. Close enough. Let's hop over here. Let's put on our 80s music. Brawl. Oh, Brawl. Where's Brawl at? Brawl was all last semester. Whoop. I got Tiny Brian on demand here now. He's in space. What are you doing, Tiny Brian? I need to make a Brawl. There we go. Tiny Brian, you're back. Good job, Tiny Brian. I know, right, Alan? It's every semester we have to make up like our own things. And then so it's really fun to me that each semester we make up our own things, because if I mentioned Brawl, it was, who was it who made that up? I'm trying to remember. Like, is it Henry? He like called it Brawl, and then we talk about Brawl on the other side of the screen. But every semester starts anew with the new memes, and so we always make up our own stuff, our own jokes, and that's why it's always fun here on Stats 101. You messed up on the alphabet thing. That's what it was. Oh man, we have so many more quotes now, Alan. I think we're up to quotes 71 or so. So you got to see, we've definitely. I love it when people sometimes they come to class and they'll start like putting in quotes. I spelled Brawl. Oh, when I was like doing my name, do you have the letters? Better data, better results. Papa John, probably. I love it. Love it. I think 70 is tacos. But that's what makes this class so much fun, and I really appreciate it. I know, better data, better results. Papa John, probably. Well, with that, let's go full Hackerman mode. I will see everybody later here on Stat 201. Bye for now, everyone. Bye for now.